Great.
Okay. So yeah, I think everything. Let's see. All right. Okay. Um, uh, so okay, so I'm gonna try to make a attempt to see if I can have also post the recording of this lectures. Okay, so this course is gonna cover basically some new or partly ongoing mathematical models for linguistics. So I'm not gonna assume any prior exposure to linguistics in any form. So what I will start doing is first of all give a very brief, very rough and not detailed overview of what linguistics is in general, what kind of things people do. And then I will in particular zoom in on a narrower part of linguistics, which is generative linguistics, and in particular study of syntax and syntactic structures. And then I'll get more into the new theory. So I've sort of toyed with the idea of starting out just with the current theory without giving any background that, just to see how that works. But in a sense, it makes more sense to try to explain why one wants to do things in a certain way on the background of what happened before that, rather than at least one should be able to see why certain things might be preferable or might give an advantage with respect to what it was being done before. And so I think we're kind of short of chairs, but I think Bill, you can grab some chair in the other room or sorry, there's another room around the corner that might have chairs. Okay, so that's the plan. So I guess probably this week and maybe for 2-3 lectures, I'll just give the very general overview, and then I'll start to move on to the more recent things. And in particular, I just want to stress the fact that it's one of the reasons for doing now this kind of class on mathematics and linguistics is because it's a particular moment in time where it's quite clear that there's going to be some very major transformations in this field that are happening and will be happening in these years, and some of which will become self-evident clear as I keep going with this class. And of course, manifestly, one thing that everybody is aware of is right now is that there's a lot of ongoing work that involves language in artificial intelligence and computer science. And as we all know, that a lot of that relies on a lot of tinkering and trying to fix things on the go, and there's a lot still to be done on the side of actually understanding what happens, what is behind those things. And so in some sense, that's also one of the things that linguistics is currently having to interface with. Okay, so but let me just take a very far side perspective, as you just in general what one means by linguistics. Of course, linguistics is in a sense the scientific study of language, and there's one important thing to mention is that when one talks about language, there's a difference between talking about language and talking about a language. Okay? It's in a sense the same difference that if you say what is life as opposed to saying what is one particular organism, and this is the way in which one should understand the difference when we talk about language and linguistics. And one thing also is that the focus one talks about language in linguistics is natural language, meaning languages that are spoken by humans or that are right now, in some sense, being implemented in machines, but it's not, other kind of language like formal languages, programming languages. So this will, because sometimes some of the tools that are used in linguistics to study human languages can also be adapted to other settings of study, right? Formal languages, programming languages, but the goal is in a sense to understand what is the structure of human languages. And the main point of view that I want to stress is that language is some kind of structure. And one of the goals is to understand what kind of structure it is. And so in some sense, this is the reason why Wine expects that this is a field that in questions that can be approached using mathematics and computationally, because that's, well, what one encounters when studying many other kinds of structures. And in a sense, the whole purpose of mathematics is to be the study of structures. And so, that's what we want to do. So languages, we all speak one or many, or or a combination of several ones, depending on the time of the day. And but there are lots of languages in the world. And the larger, so these are some of the list of some of the language families in the world. And the largest language families in the world, the Congo languages and the Austronesian languages. And many of us, of course, well, all of us, since we're here speaking English, are familiar with the family of Indo-European languages, which is, however, it is one large family and is, however, much smaller family than several of these other ones. And the list is kind of long, and there are, a large number of these families, each one of them consisting of many other languages. What exactly constitutes a family is, of course, an object of debate and study. And there's a lot of linguistics that goes into trying to understand how languages are related to one another, how they historically developed in certain ways. The distribution of languages around the world according to these various families that I mentioned is also kind of interesting. There are languages of certain families that you find in places where you wouldn't expect to find them. And like the language of Madagascar is actually one of the Austronesian languages, not one of the Congo languages, like the one of the adjacent regions and so on. So it's there's also interesting historical questions about how the geographic distribution of languages happen to be the way it is. And when it comes to relatedness, we know certain, for example, this is the Indo-European language family that we're all familiar with. And within that, there's also a lot of still open questions about especially regarding what happened to be the early branches of the Indo-European language tree. There's still a lot of unsolved problems in historical linguistics, which is the part of linguistics that deals with trying to understand the historical development of languages. And so what are the kind of questions that one asks? Well, the question that I will focus on a lot in this class is trying to understand what is the kind of fundamental generative and computational principle that allows for all this richness of human languages and for this infinite possibility of sentence formation that is in all different languages. And what are the constraints and rules that govern this generative process? What kind of principles like structure and organize the diversity of linguistic form that we see across all the various human languages, like what are the things that are common and the things that actually diversify the structures that we see. I mean, the thing is that languages can be extremely different from one another, but not arbitrarily different. There's some common structure that exists in all known human languages. And of course, other questions of linguists are interested in, how this kind of computational process of structure formation that we use in forming sentences is actually realized in the human brain. So what is like the neuroscience counterpart of the structures that one can study, and theoretically and empirically, and how is language acquired? We all learn at least one language when we are very small children, and there's a phenomena that linguists call it the poverty of the stimulus. The fact that one quickly acquires a language as a child on the basis of very few examples, and is very quickly able to generate fairly complex syntactic expressions, syntactic structures on the basis of much simpler and very few examples that one's been exposed to. So this, if you want, you can contrast this with what is happening nowadays with artificial intelligence, where there is like an enormous corpus of data that is being fed into the training of machines that are supposed to produce text language, and an enormous amount of parallel computing that goes into doing this training. And somehow, this is a highly complicated process, as we see when we try to have a machine do that. But our brain is so predisposed to the production of language that on the basis of a very minimal kind of input, this starts to produce things that are more complicated than the input that it gets. And of course, another question that has to do with biology is, of course, how our faculty of language evolved. I mean, the language is a very recent step on the evolutionary scale compared to properties of our brain, like vision, which is very ancient in evolutionary sense. So what is it that the minimal amount of structure that caused this development, and what are the other structures that are pre-existent in our brain that are involved in the process of language parsing and language formation? This is, for example, to do with how language with semantics, in the sense of how we are parse for meaning in sentences, and how that relates to other ways in which we parse for meaning, like our visual system parse for meanings in visual scenes, for example. Is that related? Is that different? And also how languages themselves change dynamically over time. We see this branching of language families, which we are all familiar with the fact that in the Indo-European language family, there are like ancient languages that are very well recorded, in terms of text, and one can see the change of language, keep track of the change of languages historically, and what are the rules, or what is the dynamics that underlines that change. Okay, so these are like many of the questions, and then there's another fact that so sort of roughly subdivides various branches of linguistics, and it's based on the idea that you can view language at different scales. It's like with physics, right? There was this very famous maybe powers of 10, where you keep zooming in or out, and you look at physics at very different scales, and it looks very different. And in a similar way, you can look at language at different scales, and the main scales at which people look at languages are the small scale structure is phonology, where the basic units that you're looking at are the units of sound that can be combined in forming words. There's an intermediate scale, like the mesoscales of linguistics, which is morphology, and they are the main units that you look at or measure is words. And so you're looking at how words are modified in languages. And the large scale structure of language, as borrowing the large scale structure of space-time, is syntax, where your basic unit of measure is sentences. And so most of what I will talk about in this class is studying the large scale structure of language. And of course, there is another level, which is in a sense global meaning. So how we use language to convey meaning. So how we encode and decode meaning out of linguistic expressions. So syntax, as I said, is the large-scale structure of language. It has the property that it's a very robust aspect of language. For example, when languages interact, the lexicon, the words that the language use, are a very flexible aspect of the language. I mean, the words are borrowed and exchanged between languages extremely easily. They circulate between languages, they change very quickly over time. But syntax is an extremely robust invariant of a language. It doesn't mean that it does not change over time. And there are very interesting phenomena that tell you how syntax has changed in languages out of the effect of interaction between different languages, but it's a very robust quality. And so interaction is slower and it's something that is much more characteristic of a language. And if it is largely responsible for the compositionality of language, the fact that we can have expression nested inside other expressions, and we can have the possibility of actually encoding complex meaning in language. So as I said, the analogy, right, is this. In physics, when you look at a universe at different scales, you also in particular expect that you will end up using different mathematical methods and different mathematical models depending on what scales you are looking at physics, right? You expect to see Riemannian geometry if you're looking at general relativity. You expect to see Hilbert spaces, and if you're looking at quantum physics. And of course, there are things that will connect different scales. You expect that if you are in the early universe or in the black hole, or gravity and quantum physics will have to interact. But so in general, you expect that every scale will have its peculiar kind of mathematical description and mathematical modeling. And the same is actually happening with linguistics. Depending at what level you're looking at what scales you're looking at language, you also will need to use different kind of mathematical tools and different kind of mathematical structures to understand that. Okay, so I'm gonna, what I'm gonna do is just give a very, very rough look at these different scales, which one considers language. And then, as I said, for most of the class, I will then focus on syntax in particular. So I said that, well, let's start at the small scales. So phonology deals with sound structures. You have certain basic building blocks, which are the phonemes that a certain language uses. And the physical aspects of how these phonemes are produced in the human voice is to do with what's called phonetics. And many languages have, in addition to phonemes, have a kind of tonal systems, which I'll say something about in a moment. There's certain so these are like descriptive, is the descriptive aspect. So the descriptive aspect is you look at different languages and you try to understand what are the basic sound structures, what are the basic rules for combining these sounds. And then, of course, there's some kind of theory or generative theory about how these different aspects of the sounds can be combined and or can be modified and combined, and whether they satisfy certain constraints of optimality and so on, they can be reproduced or modeled. And morphology, as I said, has to do with words. And then, so this is the level at which you normally encounter when you pick up a grammar of a certain language, right? You pick up a book that summarizes the grammar of a certain language. What it typically does is telling you how words are, modified in a given language, and have various kinds of word formation, how you inflection of nouns and verbs, and you have also a kind of collection of all the idiosyncrasies of that particular language, will be irregular forms or something. So morphology is kind of like the classical way that people have been studying languages for a long time. And of course, there is one thing that people have been more and more aware of, that the boundary between morphology and syntax is somehow not very well defined and somewhat flexible. There's something that now is more often referred to as morphosyntax, because to some extent you can combine into words things that really have to do with the structure of sentences. So there's somehow a kind of flexible boundary. You also see, for example, that languages that have a lot of morphology, like a lot of cases and so on, they tend to have more flexible word order in sentences than languages that are poor in morphology. So the interactions between morphology and syntax has a lot of interesting aspects. And so syntax, as I said, I'll say a lot more about it later, but is in some sense looking at the principles and rules by which sentences are formed, and why criteria according to which we decide if a sentence or not, is viable or not, is parsable or not, and so on in a given language. And so I will focus, in particular, in talking about syntax. I will focus on one particular view, which is generative grammar and generative linguistics. And that thing, I'll say more about it later, but that's a viewpoint that in some sense focuses more on what is called the I language, in the sense the internal language, rather than it's an externalized form in speech or writing. So it's like how we form language inside our brains. And I'll make an example in a moment to be more precise about what the difference is between the in I language and the E language, language. So this model, I'll say a lot more in a moment today, but I mean this way of thinking about syntax has evolved over the years. And yeah, most of this class will be about trying to present what is the current or ongoing state of the art in formulating this theory. And the other layer is semantics, which is how meaning is encoded or decoded. And this is where also connections to cognitive science and also philosophy of language and logic and other forms of computational models of semantics happen. So I will talk quite a lot about semantics too at some point in the class, especially because again there is something that is called the syntax semantics interface, which is how we are able to parse out of what the product of syntax, which is the form syntaxes. Okay, so since I say a few things that I will not come back to later, so I'll just give a little bit of the background on the things that we will not discuss any further later in the class. So what about phonetics? There are the use of sound, the basic sounds that are used in across languages can vary a lot. There are languages that have a very short supply of phonemes that are used in the formation of words, and there are languages that are extremely rich in phonemes. So they goes from about 10 in the smallest case to almost 150 in the largest cases. And these sounds are somehow mapped according to certain traditional descriptions that have to do with the position of our mouth as we pronounce these sounds. So there are certain charts, which I'll show in a moment, that somehow classify the different type of sounds that our mouth can form. And the end, not just the position of the mouth, but also the way that our breathing is used in producing the sounds. There's something also that is studying the specific rules and restrictions on arrangements of sounds within syllables in a given language. That usually goes under the name of phonotactics. And there's some very interesting things that can happen there in different languages. Certain sounds are, for example, barred from accompanying certain other sounds. There are these very interesting phenomena that are called harmony, where certain sounds are modified in language when other sounds are present or absent. And various languages have very precise rules on how this type of sound formation happens. So as I said, the various phonemes are classified, according to the shape of our vocal organs, in various ways, the positions of the tongue and the mouth. There's a kind of international, so since all different languages will necessarily use a lot of different alphabets and a lot of different conventions about how words are pronounced, there's a standard phonetic alphabet that is used to compare the pronunciations across different languages. It's called EIPA. So when you encounter words, they're usually accompanied by this commonly agreed on chart of how the sounds are expressed. And there's several charts. There are, again, for the vowels, there's a scheme that kind of represents where the position in the mouth, where the air is when the vowels are pronounced. And for example, this is the way that the vowels of English are charted in this type of standard coordinate frames of phonemes. And there's, as I said, in addition to the different kind of sounds, there are many languages in the world that are tonal. So in addition to the sounds, there are tones. In fact, most languages in the world are tonal. We just happen to be in one of the deficient language families that do not use tones. But the standard thing in most languages is to use tones. There are different kind of tones. There are mainly two different kind of tones. There's a registered tone system, which is, for example, typical of the major Congo languages, where the tones are distinguished by the pitch. And there is a contour tone system. That's a typical one of Mandarin and the Sino-Tibetan language, where the tones are distinguished by the shape rather than the pitch. And there's a lot of languages that combine both the pitch and the shape, like Cantonese is the most widely known one that has both of these tone systems combined. And it's important to keep in mind that it's not just that the tones, as in the famous example in Mandarin, the tones don't just distinguish different lexical items, but they also encode grammatical aspects of the language in a lot of languages. And there's other kind of what are called suprasegmental aspects of how tones and contour tones and level tones are expressed in this general way of describing sounds in languages. This is IPA.
This is approximate. This is still approximate, right?
Yeah, so it kind of captures most of the cases that are known in various languages. But of course, when you have combinations of different type of tone systems, it's and as I said, there are other kind of one of the interesting aspects of knowledge is that there are these long distance effects in words, and there's apparently there's like no clear bound to like how far of a long distance structures you can happen to have. There are these changes of sounds in words that are caused by the presence of other sounds. And vowel harmony is the most famous one. It happens in various languages, Turkish, for example. And there are other similar things. I mean, I recently heard the talk of someone who was studying these things, mentioning that in some of the Native American languages here in California, you have this, for example, this rule that you can never have in the same word an S and a sh sound. It doesn't matter how far apart they are from each other. So there are rules like this that govern like long distance effects inside words. And so there are kind of ways that one tries to model all these different effects that happen in sounds in words. One of them is, for example, this method of the segmental phonology. This is not particularly new. Assign certain variables and binary variables to describe all these various combinations of effects, sound effects and tone and pitch effects, and in a certain form. And then one can look at structures that keep track of the interaction between these different effects. And there's some kind of geometry of the possible interactions that one can see and study in different languages that can be realized explicitly in these terms. So you can see some various symmetries and transformations that are possible in various features in this way. So I will not cover this, but I wanted to mention this fact because we will see more and more that one identifies various kind of interesting structures that govern how various parts of language are put together, and that's how looking at how these structures can be transformed is part of what allows us to understand how language is formed and how it's used. And one thing, so there are other links that, for example, try to study various forms of optimality properties, that the way that the sound system in languages functions, and it's a kind of a dynamical system, description of some aspects of that. One thing I wanted to mention, so this is an example of some very recent work in phonology. This is just from last year, where one can see what kind of mathematical tools are applied to the study of phonology. In particular, there's some classification in terms of that encode various type of phonological patterns in terms of semigroups and formal languages, and one can describe these phonotactic patterns, for example, harmony and how long distance effects that happen in various languages in terms of this type of semigroups and string-to-string transducers. So I recommend, if you want to look at some aspects of how mathematics is used in phonology, for example, to look at some of these recent papers and see what people are doing with this. And so morphology, as I was saying, is sort of more like this classical type of grammars that we all study when we learn languages as adults. What various rules about word formation, various kind of lexemes, which are essentially like your vocabulary items, words abstracted from all the various possible forms of the same, so kind of word stems, right, that then are take on various different forms according to grammar, and various rules, inflection rules, conjugation of verbs and inflection of nouns, and various rules about word formation that allow you to combine different lexemes in single words. And there's of course, word formation is usually either a system of prefixes and suffixes that modify a certain word stem, or is just a combination of different word stems in one. Of course, some languages are extremely rich in word formation, and other languages are typically poor in word formation. Within the Indo-European languages, for example, in the ancient Indo-European languages, you have on one side, languages like Sanskrit and ancient Greek, which are extremely rich in word formation. And apparently languages like Hittite, which is also one of the ancient Indo-European languages that have absolutely no known example of composite word formation. And of course, this could have a lot to do, because these are ancient languages, right? So this could have a lot to do with what type of documents are available for these languages. The documents that we know from Hittite are always kind of bureaucratic documents. Most of the documents we have from ancient Greek and Sanskrit are poetry. So, are we really comparing the languages, or are we actually comparing many different uses of language? But in ancient Greek, you encounter expressions like "rosodactylos theos," which is a famous verse of Homer, the dawn with the rosy fingers, which is kind of a very nice composite word. But of course, this what you expect to see in poetry. It's not what you expect to see in in the trade contract about selling a piece of land. And so in the same way, right, some languages are extremely rich in the forms of, modification of words, and some have very little of that. And, the other aspects of morphology, include the breaking down of words into the minimal, smallest, grammatical units, like roots and various affixes. The fact that you can have different morphemes that play the same grammatical role. For example, in English, you have 3 different ways of making a negation in a language, and they all derive from different ways, but they all have different origins, and they all can play the same grammatical role. You have different ways of forming plural and so on, right? So these are all part of what morphology in general studies. And another thing that distinguishes languages from the point of view of morphology is how analytic or synthetic they are. So languages are very analytic if they have like a small amount of inflection, and word order tends to be more rigid. And they have fewer like morphemes per word, right? And so there's words are kind of like more isolated pieces, right? And among the more analytic, you find languages like Vietnamese, for example. And the languages are more synthetic, the more morphemes can combine in words. You can form, like, in certain modern languages, you can form very long words. Like in German, right? If you say that's a voting notification, it just becomes a single word. Or if you're talking about a landmark, in Russian is like something that is worthy of being noticed, right? That's how it works. And at that extreme, you have again, a lot of languages in the world, actually a large part of languages in the world, not the ones that we are normally using here, but are polysynthetic. And polysynthetics really are languages that combine entire sentences into single words. And again, there's various different forms of how the polysynthetic languages can function. But one thing that one already sees in morphology is the fact that you have certain ways of combining pieces that follow certain structure, right? For example, if I take a word like unfriendliness, this is obviously a composite of different things, but it's a composition that happened according to a certain rule. And if one unpacks the way that this word is formed, one finds a certain structure that tells you how these different parts of the word are combined together. And this idea that language sort of hides all these more structured levels of unpacking the information. One sees it here about morphology, but it becomes very crucial in syntax. So another part, of course, that is typically grouped together with morphology, the morphology is lexicology, which is, the actual classification of words, and, the kind of identifying like the lexical unit, the idiomatic expressions that are multi-word, but they function as effectively as a single word. The etymology of how the history of words changed, the use of words changed, how words are borrowed and shared between languages and so on. And it says, so these are kind of the aspects of language that are more traditionally studied in the old grammarian type work. And syntax is, as I said, more the large scale aspects, and where the units of structure that you're looking at are, the scale of sentences. And, you understand, the principle that governs sentence structure and sentence formation, both within a language and across languages. So, what is it that is peculiar to a particular language, and what is it that is actually universal across languages? Interestingly, although, as I said, most of the study of language traditionally was focused on morphology and lexicon, the study of syntax as a main structure of language is very ancient. One of the first attempts to a scientific study of language was in India in the 4th century before Common Era. Panini was a grammarian of the time, and the first one who systematically studied the Sanskrit language from the point of view of breaking down syntax into constituent parts and rules of composition of language. In the ancient Greek world, there was a certain amount of work of a grammarian, primarily Dionysius of Thrax, but this notoriously focused much more on morphology than on syntax. So in a sense, this crucial focus on syntax that was there in the Sanskrit got somehow lost for a long time and resurrected in modern theory. So the Saussure was one of the main, scholars of modern linguistics, of structuralist linguistics, was actually inspired by the Sanskrit work. The work of grammarian and about Sanskrit and in formulating structuralist linguistics. So there was like a huge step back into recovering the old work and formulating the modern language. So the modern syntactic theory that I mostly will talk about is actually following the period of structuralism, and is the part of linguistics that, as I said, goes generally under the name of generative linguistics. And is focused on I language versus E language, so that kind of internal mental language, as opposed to this kind of community-based shared record of language, and on understanding our judgment of grammaticality. What is it that makes us decide when a sentence is well formed? And the rules, the production rules for generating grammatical sentence, and in some senses based on a kind of working assumption that we have built in our brain. There is a kind of syntax calculator, something that allows us to make this kind of construction of syntax regardless of which specific language we end up learning. We know that there's nothing that connects us as specific human being to one or another particular languages. People of different ethnic backgrounds can learn any arbitrary language. It only matters which language they are as children when they are in the process of language acquisition. So there is like a common that our brain handles language, which is independent of which specific language we end up learning. And so there is something that can be studied in itself as our faculty of language, which is universal, the human and specific language independent. Okay, so as I said, this idea about a universal grammar is a working hypothesis. There's many people have over the years put out the question of whether it's a falsifiable theory or not. In a sense, we do not have at present a neuroscience counterpart for this universal grammar hypothesis. So in that sense, there is no neuroscience experiment that you can run at this stage to test whether this is a valid hypothesis or not. And so it is assumed as a kind of working hypothesis behind how you think about language. Okay, so let me get on to the next set. Okay, so let me focus more specifically on generative linguistics, which is after this very brief overview of the whole picture, and is focus a bit more specifically on generative linguistics per se. So this particular field of linguistics has at this point a pretty long history, but of course, there've been a lot of people working in this field over the years, so who have contributed significantly to the field. But in itself, it was initiated and developed by Noam Chomsky starting in the early 50s, in fact, 40s and early 50s. And it went through several different stages of development. There is, well, it's a remarkable fact that you have, it doesn't happen often that you have a field of science where you have a continuous stream of breakthrough coming from the same person for 70 years in a row. So it's a quite remarkable story in that respect. But so the main, I just want to point out just the main steps, the development of this field. So somehow at first phase, that was mostly in the 50s and 60s, which gave rise to the theory of formal languages, which is now just a part of mathematics per se. It has a lot of applications to computer science as well. But it was somehow constructed as a first attempt to actually create mathematical models for the generation of syntax in natural languages. That sort of evolved, especially in the 70s, into slightly different. It was called transformational grammars. And which is sort of attempt to combine aspects of formal languages with another point of view, which is that of transformations. I'll say something about later. The next sort of step in this development of the field happened in the 80s. There's a part of the theory that goes under the names of principles and parameters and government and binding. And one of the ideas, the interesting ideas of that I will say more about later, is also the attempt to come up with a good parameterizing method for comparing at the level of syntax different languages. So this is the concept of parameters, in particular what linguists call syntactic parameters. It's kind of the idea is to come up with a set of binary variables that are designed to answer yes/no questions about whether certain kind of syntactic constructions are possible or not in a language. And that will give you a way to compare, at the syntactic level, different languages by comparing these parameters. And there are still some major open questions in that perspective. And of course, the main open question that's been open since the 1980s is actually what is a good
complete set of variables for the purpose of encoding the syntax of a language. There's a few hundreds of these, 0-1 variables that are known and classified by linguists. But it's also well known that they're not independent variables, and know that some of them affect the others. So there are lots of relations between them. There's relations that are explicitly known to linguists, and there's relations that are visible in the data, but not explicitly, whose functioning is not explicitly understood. And so because of that, it's clear that the actual number of independent variables should be much smaller than the ones that are currently used. But so this is a mathematical question per se, right? What is a good set of variables that can actually classify the syntax of language and allow for comparison between different languages? So I'll come back to say something about that later. And government and binding is a sort of series of syntactic rules that one can use to test the grammaticality of sentences, and I'll also say something more about that later. But somehow starting in the early 90s, there was a kind of further conceptual change in the field, and the idea was to kind of try to simplify the description of how the generative process of language happens. And in some sense, one of the questions, right, is where the one I mentioned before, the fact that language is a fairly recent evolutionary development, and in evolutionary scale, it happened in a really short amount of time. And for that reason, it shouldn't depend on a large number of changes that had to happen, right? And so somehow it has to depend on something that's very simple and very essential that made this syntax calculator possible, right, in our brains. And so this the idea of minimalism. So we're trying to identify what is the key structure in the computational process of syntax. And this, in turn, underwent a further, redevelopment in these past 10 years. And so what I will actually focus on out of this really, really long history is actually what happened during these last 10 years, and actually in particular what happened during the last year. Okay. But in order to do that, what I will do is go through, again, like I did, a very, very quick overview of the other aspects of linguistics that I'm not going to talk about in this class. I will do a very brief overview of the other aspects of the theory of generative linguistics, of the history of the theory of generative linguistics that I will not talk about in this class, but that somehow serve as a kind of background to understand why one wants to modify or try to present the theory in the way that I will talk about later. Okay, so here's some of the very, very general aspects of the idea of generative linguistics. And okay, it starts from this observation that language as is produced by the human brains is a complex and a very highly structured phenomenon, and one wants to be able to try to model the production, acquisition, and parsing of syntactic structures. And again, the main focus of generative linguistics has always been on syntax, but this doesn't mean that the same methods and the same kind of models have been also adapted to use in phonology and morphology and morphosyntax, and there's some kind of generative models of semantics as well. And so I will kind of occasionally mention some of these things. But I mean, the key question is what is the fundamental generative process of language? And that's called the generative grammar. A model for that is what is called the generative grammar. So here, I mean, the word grammar is not meant in the same way in which it's traditionally meant, right? The word grammar means this grammar book that has to do with describing the morphology and all the idiosyncratic peculiarity of a particular language. this in some sense is like the opposite view. Grammar is like a computational mechanism or a computational description that should be giving you the underlying model that is behind the difference between, is prior to the difference between languages. Okay. And of course, this brings up some very general and somewhat philosophical kind of questions, like what does it mean to model something? Right? And what does it mean to explain? This is sort of, in a sense, a fundamental question about what is the nature and the purpose of science. And it's not of course, one could have like a whole, philosophy of science, class just discussing these questions, which I have no intention of doing. But it is relevant. It is especially relevant today because of the developments that are ongoing in artificial intelligence, where one can build machines that are good at predicting, at giving, have a good predictive power, right? You can see the current status of, if you to play with the current, large language models, they are very good at, predicting the next word, right? In a way that's, compatible with our understanding of language, and it's highly compatible with the way that humans handle linguistic text. But in a sense, that's where this question is interesting, right? Because what is the purpose of being predictive in science? The point of, so the purpose, the prediction is not the goal. That's it's maybe not such an obvious point, but I mean, the prediction is not the goal. The prediction is what makes your theory falsifiable. So the thing that is the goal of science is the explanation, is the explanatory power. And the point is that you want to make sure that your explanation is testable. And that is the reason why you want your theory to be able to make predictions, because you want to make sure that whatever you are trying to explain is explained in a way that's consistent with the facts. And this, in a sense, is the point, because suppose that you have an 100% accurate and reliable simulation of nature, which is not explanatory at all. Well, you already have one, it's nature. The point of science is to understand it, not to replicate it. Okay? So this is a reason why there is something that is in the present state. Of course, these things are very rapidly developing, but in the present state of the way the language is studied in the context of artificial intelligence, is something that's very disturbing, which is the fact that you have a predictive machine that is completely non-explanatory. And so you would like something that is both explanatory and predictive. Of course, you don't want to have something that's explanatory and not at all predictive. Otherwise, it could you would have no way to know what you are, if you're talking about, makes sense or not. Right? Okay, so this is in a sense what one would like to be able to obtain, something that is a model that is explanatory and would have some to say about the way that language functions in our brain. So if that is the goal, well, why is mathematics? So why am I here? In other words, so I should justify my existence in this matters. Well, so as I said, mathematics is by definition the science that deals with the study of structures. Of course, if you stop the first person in the street and you ask, what is mathematics? The first chance is that they will run away. The second chance is that they will tell you that it has to do with numbers. And well, yes, yes, occasionally it does, but yes and no, in the sense that the only reason why numbers are of interest to mathematics is the fact that numbers exhibit interesting structures. Right? I mean, let's think about prime numbers, right? Prime numbers are the typical example of something that is of interest to mathematicians because it has a very interesting structures. We don't know, how prime numbers are distributed among the integers. And there are this ends up being related to a lot of other very interesting structures in mathematics. Why the Riemann zeta function says its zeros on the critical line, if it does, and so on. Right. So that's the reason, in the sense in which numbers are an object of study to mathematics. And so yes, numbers have interesting structures, and so does language. And so language is also a perfectly viable object of study for mathematics in the same sense. And also there is another point that can be made, is that the understanding of more and more interesting and elaborate mathematical structures have played a fundamental role in the development of theoretical physics throughout the 20th century and continuing, nowadays. Theoretical physics had motivated the development of a lot of mathematics and has in turn benefited from the development of a lot of mathematics. And in the same way, one could hope that a similar interaction, of course, the interaction between mathematics and theoretical physics is very old and has had a lot of time to develop. But one can hope that in a similar way, the study of mathematical structures and more interesting mathematical structures could be brought to have relevance and the study of linguistics, and conversely, the specific problems of linguists are interested in can motivate mathematical structures to look at. This is actually the principle that was advocated already a long time ago. There's this book in the early 80s, Chomsky wrote a presentation that exactly makes this point, that linguistics should be studied with similar principles and methods as theoretical physics. So that's exactly what I'm planning to do in this class. So let's just get down to earth a little bit and see what do I mean when I say that syntax is a structure. So let's take this famous Groucho Marx joke. I shot an elephant in my pajamas. What it was doing in my pajamas, I will never know. So why is it funny? The reason why it's funny is because it's conflating two different structures, right? And there is one of them in which in my pajamas is modifying a noun phrase, which is an elephant. So it's an elephant that happens to be in my pajamas for whatever reason that we don't know. And I shot such an elephant that happened to be in my pajamas. But of course, the most conventional parsing of the sentence, I shot an elephant in my pajamas, is that in my pajamas is modifying the action of shooting. Instead of shooting in the dark or shooting last night, I actually was shooting in my pajamas. And so the point of these examples is that a sentence is not just a sequence of words. The trick here is the fact that what we perceive is the structural relation among those words rather than the string of words itself. And the fact that we can perceive is like this, sometimes you have these optical illusions where you have simultaneously two different ways of parsing the same image, and your brain sort of flips between them. So you have a similar phenomenon here. You have two different ways of parsing the structure of this sentence, and the joke is making you flip between one and the other. And so this is somehow a very key observation that is underlying the entire perspective of how one studies syntax. That our brain, although the way that we handle language because of the way that we are physically designed is through a string of words, because that's the way we speak, that's the way we hear. Even languages that are not based on speech, like various sign languages that have their own rich syntax, are still based on a time-ordered sequence of events, a time-ordered sequence of signs. And writing is also a time-ordered sequence. So we are sort of forced by the physical limitation of the way that we can use language to, producing it and receiving it as strings. But that's not the way that we parse it. The way that we parse it is as structures.
So is this kind of representation a model of how we parse it, or how the meaning of the sentence? Because it means both. So is it some kind of combination of both of these?
Right. So you could say that if I'm only given this string, right, I have two possibilities. I have two possibilities for parsing this sequence, and they correspond to these two different structures. If I give you the structure, then that makes it well defined. I mean, it's another example like this. If I say I saw someone with a telescope, again, you have two different parsing of what this sentence means. And again, they correspond to two different tree structure that have, so sometimes the point is that when you are at the producing end of language, you kind of, your brain builds a structure and then you externalize it as a string of words. When you are at the receiving end, you receive the string of words, and so you have to kind of, parse for a structure, which, part of your understanding of a sentence is, being able to produce the parsing and identifying which is the relevant structure that's underlying that word. And it's interesting that there's a lot more information, right, in the structure. So it's kind of, you're trying to like solve this type of inverse problem where you're only given this flattening out of the structure into the string, and you're trying to construct the part that has been projected out. And this is, in a sense, why, again, coming back to what is happening now in the context of artificial intelligence and so on, all the functioning of I'll actually talk at some point about, the large language models, how they work, and how this is related to our understanding of how syntax works. But, these structures handle strings. So they're designed to only handle strings. And so, but because they will have to produce text, right? They will have to somehow manage the calculus of syntax. And so the part of the process that the machine has to do is trying to at least partially solve this inverse problem of constructing the computational mechanism of syntax only out of this data of strings. Okay, so one thing that so I'm gonna like go back to the beginning of the story of generative linguistics, and so I'll start out to say how the theory of formal languages came into the field, and why that was for some time a way of thinking about the generative structure of language. So one observation first is the fact that language is capable of creating infinite recursions. Now, this is a very important point where one has to distinguish between the concept of I language and the concept of E language, because of course, in an actual spoken text or in an actual written text, everything is always going to be finite. And however, so in any language, like in English, one of the simplest example that you can create of a recursion is the fact that, for example, I can help someone, help someone, help someone. Okay? Of course, in practice, you will never go beyond like if you go after a certain number of iteration, it becomes funny, and then of course it would just never be something that is actually. But the point is that your brain immediately understands three things: that this sequence can continue. Okay? And I mean, your brain has no doubt on the fact that it can continue, even though you don't externalize it like that. Right? And it also, your brain immediately understands that it will continue to be grammatically correct. It will not stop being grammatical between the 43rd and the 44th iteration. Right? And also, it will continue to be meaningful. So these things are something that our brain immediately understands, even though we don't externalize these as infinite sequences. But so the part of the I language that infinite sequences and infinite recursions can be generated. And so, of course, this in itself is the telltale sign that there is an interesting computational process going on, the fact that it can generate infinite recursions. So one of the first questions that we can try to ask is, can one understand better what kind of recursions exist? What kind of recursion can be constructed?
So what is grammatical correctness? What is grammatical correctness?
In the sense of how do you know that it remains grammatical? Or?
I mean, are you just using it in the colloquial sense, or?
Yeah, so at the moment I'm just saying, like, you kind of, I mean, I'm just saying that your brain, has this immediate, when I say, okay, you can make a recursion, like you can help someone, your brain immediately understands that if the first 2 or 3 of these iterations are grammatical, they will not stop being grammatical if I add another one.
But you mean grammatical in a morphological sense?
Yeah, at this point, I just mean grammatical in a morphological sense, but let's say well-formed, in the well-formed within the language, as a more general concept of what I mean by grammatical. Okay, so this was this observation about the existence of recursions, sort of the early motivation for the development of this theory of formal languages. So formal languages are a mathematical theory that describes strings of words as produced by certain kind of computational mechanisms, so by various classes of automata. And different classes of, so there's a classification of types of formal languages and a corresponding classification of the type of automata that can compute this type of formal languages. This is one of the first main theorems in the theory of formal languages, and it's called the Chomsky hierarchy. And the thing that relates this classification of formal languages and automata to the point of infinite recursions is that different kinds of recursions are possible within these different classes of languages. And then, of course, these classes of languages, in this formal sense, they don't just include human languages. In fact, most of these examples in these classes are not human languages. They are abstract things. They can also be programming languages. They can be presentations of discrete groups. I will give examples of that. There's actually some interesting theorems on what type of formal languages you can obtain from discrete groups. And so they don't actually necessarily have to do with human languages, but they can include the case of human languages. And so one of the questions then is, like, what class of formal languages is suitable for describing human languages? So what do I mean by a formal language? So the definition is a grammar, and it's usually presented as a quadruple of two sets. One of them is called the non-terminal symbols, and one of them is the terminal symbols. And the terminal symbols you can think of as the actual words in a language, if that's the case. So things that once you reach that point, your final result would be a string of terminals, which would be like a string of words in your language. And the non-terminal are like the intermediate steps in the derivation of your string of words. And then you have a certain start symbol, which is the beginning of your derivation, and you have a set of production rules which tell you how to go from one step to the next until you've reached a string of terminal symbols. And so a language produced by such a grammar is a string. So what I mean by this is arbitrarily long sequences of in the alphabet given by the terminal symbols. And so these are like finite strings of arbitrary length that can be obtained as a string of application of production rules, starting from the initial symbol. And here's a simple example. Okay, so I give you a grammar that has a start symbol and another non-terminal symbol, this capital A, and it has two terminal symbols, A and B, small a and B, and it has the following production rules. So these are all the possible moves that you can make in the course of creating a word in this language. And so here's an example, right, of a possible derivation. So in any derivation, you don't necessarily have to use all these rules, but you have to use one or more of them in combination. So for example, no, I always have to start with my start symbol. And so the first rule that I'm applying is this. So at the next step, I have created a sequence like this. And now here I can apply now this rule here. And now I get a terminal. So from this, I don't continue anymore. And here I can apply this other rule, and I get a sequence like this. And then I can apply this rule like here. And then I apply this rule here. And now, I mean, I can just read off all the leaves of this tree in this order. And so I have shown that this sequence AA, BB, AA is in the language computed by this grammar. Okay, so that's the way that it works. So as I mentioned, one of the early, the main theorems in this theory of formal languages is the Chomsky hierarchy. It identifies 4 different types of formal languages. The most restrictive one is this type 3 regular grammars. And there is a corresponding machine recognition theorem that tells you that all the regular grammars, I'll say in a moment more about what these are, but I mean, all the regular grammars can be computed by a very restricted kind of automaton, which is called a finite state automaton. The slightly larger class is context-free grammars, and I'll say in a moment something about the production rules of context-free grammars. And these are computed by a larger and somewhat more complicated class of automata, which are called, in general, non-deterministic, but like push-down stack automatons. So these guys have no memory. There's basically these are basically Markov processes on a directed graph. And these ones have some amount of memory. This is what this push-down stack is doing. So there's a memory, but it's a memory where you can only accept what's on the top, what's at the top of the memory. You can take something out and put something in, but you cannot accept, you can only like last in, first out, but you cannot reach directly what is at the bottom of the memory. And a much larger class of languages, of formal languages, is the context-sensitive grammars. And these are computed by a much bigger class of automata, which is linear bounded automata. It is basically Turing machines, but with a bounded tape. And then, well, there's just computability. The larger class is just anything which is Turing computable. So let me just say, I'll come back. I'll give you more detail. I'll just give like one more lecture on the whole theory of formal languages, because that's something useful to know about, regardless of the specific application to syntax, because they're used in a lot of other fields, especially in theoretical CS. But so I will say more in detail. A lot of things about this theorem, but let me just say something about the difference between context-free and context-sensitive production rule. So context-free, what the name means, right, is that if I have a rule of this form, I can replace a non-terminal symbol with something else, which can be some combination of terminal and non-terminal. It means that wherever I see A, I can apply this rule. Context-sensitive means that I can apply this rule only if A happens in a certain context. So it's something that is not just seeing like the local application, but it's seeing some kind of window around it. And that is going to tell you what, so it has some local conditions, but are not just pointwise condition on when you can apply it. And so very early on, there was a first conjecture that was that the context-free formal languages would be enough to characterize the syntax of human languages. And it also, as I said, it also characterizes other kinds. So for example, there are programming languages that are known to be in this class, and there's other formal languages that have nothing to do with human languages. But the idea was that the generative aspect of syntax of human languages would be captured by context-free grammars. So, as I will say more, I'll come back to this conjecture in a moment. So for the moment, I'll give you with the suspense of whether that is true or not. And let me just say, I will talk more about this, but I'll just say a couple of words about these various automata that compute this kind of formal languages. So as I said, a finite state automaton is really just a memoryless walk on a directed graph, and where you can start from an initial state, on your automaton, and you have a choice of certain moves that you can make by following the arrows of this directed graph, and then you read off the labels on these arrows, and this gives you the words that are computed by that language. So, any arbitrary path in this directed graph is a word. Okay, so this is like the simplest kind of thing that you can do. And the case of the push-down stack automaton is slightly different. So you can still model it with a directed graph, but now the labels on the paths that you take are also keep into account the fact that you can retrieve something from the top of the memory of your stack, and that tells you which transition you're making, and you can put back some information at the top of the stack that you will use then to make some other transition. And so this is no longer memoryless, because you can keep track of where you were before by what you had deposited at the top of the stack at that step in the process. Yes.
Are you only loading one piece of information at the top of the stack at the time?
No, you can deposit a string. You can deposit a string so you don't have a fixed length for the string that you can deposit at the top of the stack. But the point is that you can always just deposit the string or take something out of that string, but not access what's at the bottom of the stack. You can always just access the symbols that are at the last in, first out. Okay, so what about the fact that I was saying that different recursions? So I'll come to what happens with this conjecture about the context-free grammars. But in order to understand what happens there, the key point is what I was saying, that different kind of formal languages have produced different kind of recursions. So here's the first example. So this kind of regular languages, this most restrictive one that correspond to the finite state automata, are able to produce, for example, infinite recursions of this kind. So I'm writing it here so that my terminals are 0, 0, and 1, so I get binary strings as the result. And this is a regular language. One can realize this as a finite state automaton, and it gives rise to this kind of. So basically, it says that your graph has two loops, right? At the different point. And the thing is that if you are in this kind of memoryless paths on a graph, and you have two loops, obviously the number of times that you go around one of these loops has nothing to do with the number of times that you go around another one of these loops, because you have no memory. So you cannot keep in mind how many times you've gone around the first loop and use that to bound the number of times that you go around the other loop. So you will be able to generate this where M and N are completely independent of each other, but you will not be able to, for example, generate this where you want to go around the same number of time on these two loops. And indeed, this is an example of the type of recursion that you can realize with the type 2 context-free grammar, but not with a regular grammar. So I will finish here so that next time we'll see why. I will actually tell you right away. The answer is that conjecture is false. And the context-free grammars are not enough to capture the syntax of human languages. And so how do you prove that it's false? By proving that by exhibiting examples of actual human languages that admit a recursion that is not computable by a context-free grammar. So a kind of recursion, like in this case, I'm showing a recursion that is computable by a context-free grammar, but not by a regular grammar. So I'll show you next time a recursion that is computable by a context-sensitive grammar, but not by a context-free grammar. And that actually occurs in, well, the first examples that were identified were Dutch and Swiss German, in which there is such a recursion. I'll show you why there's that. And so that shows that, that exhibits by counterexample, the fact that the conjecture is false. Okay, so I'll finish that next time.
Having Dutch in the context.
Thank you.